In this video, we're going to be learning about why the homogeneity of the field is important. Let's go back to that free induction decay experiment. Here we see the signal decaying away with time in this time domain representation of the data. And in the right-hand panel over here, we see the Fourier transform, which shows the spectrum. This is the frequency domain. And the width of that spectrum is related to the rate of decay of the signal. The faster the decay, the broader the spectrum. So why does that signal decay away? Well, one thing we know is that eventually the spins do have to go back to thermal equilibrium along the magnetic field. So there has to be some eventual dying away of the signal due to that process. But if we look at this carefully, we can see in fact that the rate of decay turns out to be a lot faster than that which we would expect from a return to thermal equilibrium alone. So what's the reason for that? It turns out to be related to field inhomogeneity. Let me try to explain that to you. Suppose we have a field that's perfectly homogeneous, and we consider two atomic nuclei in different positions in that magnetic field. Well, they'll have exactly the same Lahm or precession frequency. So the magnetization vectors associated with those atomic nuclei will precess at exactly the same rate. They'll stay in step with each other. But now imagine the magnetic field is inhomogeneous. That means it varies from place to place across the sample. So atomic nuclei in different positions are going to have different Lahm or precession frequencies. One might be faster, one might be slower. So that means that when we do the free induction decay experiment, the magnetization vectors start together in phase, but because of their different precession frequencies, the vectors gradually spread out. So that the total magnetization, which is a sum of these two vectors, is smaller as a result of them spreading out. And that's the reason for the decay. Now I can demonstrate that to you in a very simple experiment. And to do so, I'm going to use this crescent spanner over here. Now this spanner's definitely got some magnetism associated with it. So if I were to bring it close to the probe, it would definitely disturb the homogeneity of the Earth's magnetic field. So what I want to do is to repeat the free induction decay experiment with the spanner nearby. Let me do that. Pre-polarizing pulses on now, hold the spanner there, and here's the free induction decay. Look at that, it's very rapid indeed, and it's led to a very, very broad spectrum. So by perturbing the homogeneity of the field quite severely with this crescent spanner, we produced a much more rapid decay and a much broader spectrum. Now the area under that spectrum is exactly the same. It's related to how many atomic nuclei we've got in our sample. So if the spectrum is made broader, it means that the height of the spectrum is going to be much smaller to conserve the same area. And that lowering of the height of the spectrum makes the noise much more visible. So we have a much noisier looking spectrum than we had before. I've got the spanner back on the table now. Let's repeat the experiment to see if we return to the initial condition. There's the signal, and you can see the same rate of decay that we had when we started, returning to a much narrower spectrum. So can we do a better job? Can we improve on the homogeneity that we've got at the moment? Well, it turns out that we can, because inside the Terra Nova probe is this set of complicated looking coils known as magnetic field gradient coils. And what they do is to provide a magnetic field that varies linearly in three orthogonal directions, so that by putting a small amount of current in these coils, we can correct for imperfections in the Earth's magnetic field. And the Terra Nova is set up to do that through the software. We have these little slider bars here that enable us to adjust the currents. And I've previously set up the currents to produce just the best homogeneity we can with this apparatus. And I'm going to reset the current settings to those values. So let's run the free induction decay experiment again. Here it is, and look how much longer it is. a much longer free induction decay in the time domain, and consequently a much narrower spectrum in the frequency domain. So the real advantage of homogeneity is that we produce higher resolution and better signal to noise. And this process of adjusting currents in gradient coils is known as shimming. Shimming is the trick by which we can improve the homogeneity to get the best result possible. It turns out that there is another way of compensating for inhomogeneities in the Earth's magnetic field, and that's known as the spin echo trick. In the next video, we'll be looking at that.